We are made of stardust, the saying goes, and a pair of studies including University of Michigan research finds that may be more true than we previously thought. The first study, led by researcher Jackie Lee and published in Science Advances, finds that most of the carbon on Earth was likely delivered from the interstellar medium, the material that exists in space between stars in a galaxy. This likely happened well after the protoplanetary disk, the cloud of dust and gas that circled our young sun and contained the building blocks of the planets, formed and warmed up. Carbon was also likely sequestered into solids within 1 million years of the Sun's birth. Which means that carbon, the backbone of life on Earth, survived an interstellar journey to our planet. Previously, researchers thought carbon in the Earth came from molecules that were initially present in nebular gas, which then accreted into a rocky planet when the gases were cool enough for the molecules to precipitate. Lee and her team, which includes astronomer Edwin Bergin, Jeffrey Blake of the California Institute of Technology, Fred Chesla of the University of Chicago and Mark Hirschman of the University of Minnesota, point out in this study that the gas molecules that carry carbon wouldn't be available. The condensation model has been widely used for decades. It assumes that during the formation of the Sun, all of the planet's elements got vaporized, and as the disk cooled, some of these gases condensed and supplied chemical ingredients to solid bodies. But that doesn't work for carbon, said Lee, a professor in the Department of Earth and Environmental Sciences. Much of carbon was delivered to the disk in the form of organic molecules. However, when carbon is vaporized, it produces much more volatile species that require very low temperatures to form solids. More importantly, carbon does not condense back again into an organic form. Because of this, Lee and her team inferred most of Earth's carbon was likely inherited directly from the interstellar medium, avoiding vaporization entirely. To better understand how Earth acquired its carbon, Lee estimated the maximum amount of carbon Earth could contain. To do this, she compared how quickly a seismic wave travels through the core to the known sound velocities of the core. This told the researchers that carbon likely makes up less than 0.5% of Earth's mass. Understanding the upper bounds of how much carbon the Earth might contain tells the researchers information about when the carbon might have been delivered here. We asked a different question. We asked how much carbon could you stuff in the Earth's core and still be consistent with all the constraints, Bergin said, professor and chair of the Department of Astronomy. There's uncertainty here. Let's embrace the uncertainty to ask what are the true upper bounds for how much carbon is very deep in the Earth, and that will tell us the true landscape we're within. A planet's carbon must exist in the right proportion to support life as we know it. Too much carbon, and the Earth's atmosphere would be like Venus, trapping heat from the Sun and maintaining a temperature of about 880 degrees Fahrenheit. Too little carbon, and Earth would resemble Mars, an inhospitable place unable to support water-based life, with temperatures around -60. In a second study by the same group of authors, but led by Hirschman of the University of Minnesota, The researchers looked at how carbon is processed when the small precursors of planets, known as planetesimals, retain carbon during their early formation. By examining the metallic cores of these bodies, now preserved as iron meteorites, they found that during this key step of planetary origin, much of the carbon must be lost as the planetesimals melt, form cores and lose gas. This upends previous thinking, Hirschman says. Most models have the carbon and other life-essential materials such as water and nitrogen going from the nebula into primitive rocky bodies, and these are then delivered to growing planets such as Earth or Mars, said Hirschman, professor of Earth and Environmental Sciences. But this skips a key step, in which the planetesimals lose much of their carbon before they accrete to the planets. Hirschman's study was recently published in Proceedings of the National Academy of Sciences. The planet needs carbon to regulate its climate and allow life to exist, but it's a very delicate thing, Bergen said. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.